Hello and welcome to today's video. In this video, we are finally going to apply our knowledge about integration to compute some actual integrals. So this video is titled Integration Examples. And as you would probably expect, it consists of examples. So here we go. First example, a simple one to start you off. Let's say we want to compute the integral from -1 to 1 of the term x squared plus 2x minus 3 dx. How do we go about that? Well, the first thing we do formally is we apply the linearity property of the integral. So we split this up into the sum of simpler integrals. Specifically, we can split this up into three terms: this, this, and this. And then we can also take out the constants. So for x squared here, there is no constant. That means we have the integral of x squared dx from -1 to 1. Then we need to add the integral of 2x. And of course, here we can take out the constant 2. So that's the same as 2 times the integral of x dx from -1 to 1. And finally, we have this term -3 here. So that's the same thing as -3 times the integral of 1 dx from -1 to 1. And now we can compute antiderivatives. As you know, we have to find functions that have the property that their derivative is the term in the integrand here. How do we do that? Well, we apply our knowledge of differentiation. We take a good guess, and then we can just differentiate that guess and see if it really works, and if necessary, do a few corrections. So the idea now is to take the antiderivatives, and we start with that first term here, x squared. Now, if you want to obtain x squared, we need some term that contains an x to the power of 3, obviously. So let's try that first, x to the power of 3. If we differentiate that with respect to x, then what we get is 3x squared. So not quite x squared yet, but 3x squared. Well, if you want x squared, then what we have to do is we have to divide this term by 3. And that yields the correct antiderivative. So basically the idea here is to do the opposite operation to differentiation. We increase the power here by 1 instead of decreasing it. And we divide by the new power, because when we differentiate, that new power will be the one we take in front of the expression. So we have to divide by that to make up for that. Okay, so here we have the antiderivative x to the power of 3 divided by 3. Then for the second one, 2 times, now we need an antiderivative for x. A good first guess would probably be x squared. Now if you compute the derivative of x squared, we get 2x, so similar to what we just saw before, we have to divide that by 2 to get x. So here we have 2 times x squared over 2. And finally, we have -3 times, and the 1, well, that's easy. If you want to find a function that differentiated yields 1, then we would try the function x, and that already yields 1, so we're good. You don't have to modify anything. So the antiderivative of 1 is x. Okay, so this here is our integration so far. And now we just have to do the computations. Remember, this here is shorthand for evaluate this function at the upper bound and then subtract this function evaluated at the lower bound. I will use just that now. So here for the first part, we get 1 to the power of 3 over 3 minus 1 to the power of 3 over 3. Then we get plus 2 times, same thing for this expression here, x squared over 2. So that's 1 squared over 2 minus 1 squared over 2. And then we have minus 3 times x. So minus 3 times 1 minus 1. So what do we get all together? So here we have 1/3 minus 1/3. So that's a plus 1/3. Then we get plus 2 times. Now this is 1/2 minus 1/2. And here we have minus 3 times 1 plus 1. So that's 2/3. 1/2 minus 1/2 is 0. So we get plus 0. Minus 3 times 2, that's 6. 2/3 minus 6, that is 2/3 minus 18/3 or minus 16/3. And that's the final result of this integration. And of course, you don't have to do it in that many detailed steps. You could also just take this one here, do this implicitly, and then write that all into one bracket, right? Like x to the 3rd over 3 plus 2x squared over 2 minus 3x, and evaluate that expression all in one go. And that's the way we'll do it from now on, of course. Okay, let's have a look at some more integrals for other function types as well. Part B. Our next example is going to be, we want an antiderivative of the function e to the power of minus 2x dx. And I'm just going to compute an antiderivative. I'm not going to bother with the boundaries here. So, well, you know that when differentiating an exponential function, you basically get back that exponential function. So a good first guess might be to just try differentiating the integrand itself. That will yield e to the power of minus 2x, and then we have to apply chain rule, and that means we have to differentiate that expression too, and that yields a minus 2. So that's the derivative here. And that means we need to get rid of that minus 2. And of course, we can do that by simply dividing by minus 2 here and here. So, in other words, the antiderivative that we are looking for is minus 1 over 2 e to the power of minus 2x. And then as we are looking for the general antiderivative, we're just adding a constant. So that's the set of all possible antiderivatives. Okay. Another example, similar idea. What about trigonometric functions? Let's have a look at those. So if you want to integrate, for example, the sine of pi x dx, we'd use the very same idea. We want a function that differentiated becomes the sine. And of course, one possible candidate for that is a function that somehow involves the cosine. So I do something like, let's try the cosine, and we can't change the argument, so we need to try the cosine of pi x probably. Now the derivative of the cosine is the negative sign, so we get minus sine of px. And again, we need to apply chain rule and multiply by the derivative of this argument here, pi x, and that derivative is pi. So we get minus pi sine pi x, which means we're almost there. What we need is sine pi x, so this minus pi is a little inconvenient, and of course, as before, that's just a constant, so we can divide everything by minus pi. And still get a valid result. And that means the antiderivative that we were looking for is minus 1 over pi cosine of pi x plus a constant. So that's how it works for elementary trigonometric functions. D. Let's see about negative powers. What about a function of the kind x to the minus 3, for example? Well, what do we need to get an x to the minus 3 if we differentiate? You will remember the rule here is pretty much the same as for positive powers. If you differentiate, you always reduce the power by 1. So if you want to arrive at a power of minus 3, you have to differentiate x to the power of minus 2. So we need an expression that is something like this here. Now if we differentiate that, we get minus 2 x to the power of minus 3. And again, we're almost there. We need to divide by minus 2 to actually get x to the power of minus 3. So the antiderivative we're looking for here is minus 1 over 2 x to the minus 2. And again, plus an arbitrary constant. Or you could also write this, just as a side note, you could also write this as 1 over minus 2 x squared plus c. Now there's one exception to the rule that you need to be aware of, and that is the integral of x to the minus 1, or 1 over x dx. You cannot just say, well, that's the derivative of x to the 0. That's not true. X to the 0 is 1, and the derivative of 1 is 0. So that will not work. Instead, a valid antiderivative here is the logarithm. As you know, the derivative of the logarithm is 1 over x. So that is the one exception that you need to pay attention to. And that is especially important if you have an expression that involves a general power, like an integral of x to the minus k or something, or x to the k. Be sure to treat this case here, 1 over x, as a special case, and also the case x to the power of 0, of course. Okay. F. Let's have a look at the final class of functions. What about square roots? So we want to integrate the square root of x dx. How do we do that? Well, the idea is the square root can be written as x to the power of 1 over 2. And then we can apply our differentiation rules once again. If you want to differentiate a function and come up with a power of 1 over 2, then that means we need to start with x to the power of 3 over 2. So something like this, 3 over 2. If we differentiate that, we get 3 over 2 times x to the power of 3 over 2 minus 1, so 1 over 2. So almost there. What we need to do is we need to get rid of this 3 over 2 to get just this term here. And to do that, we just multiply with the inverse 2 over 3. So that is the antiderivative here. It's 2 over 3 times x to the power of 3 over 2. Or if you want to write this in terms of square roots again, that's 2 over 3 times the square root of x to the power of 3. Or simply 2 over 3 times x times the square root of x, whatever you prefer. So that's been a couple of examples for antiderivatives of functions. And of course, we should also add plus c here, right? The last example is about an application of the integral that started it all off, namely determining an area. And what we want to do is we want to do the following. We want to determine the area between the x-axis and a graph of a certain function. And the graph of, let's call that f of x, and that's a function 1/4 x squared minus 1. And of course we need to bound the interval, so we want to have this in the interval from -3 to +3. Right, so that's what we are looking for. And if we're looking for the area, remember, you have to take the sign into account. Just integrating that function over the interval will get you the sum of signed areas. So if the graph is above and below the x-axis, somewhere in that interval, then you will not get the area because parts of that will cancel out. What you have to do is, in fact, you have to integrate over the absolute value of x. So what we need is the integral over not f of x, but the absolute value of f of x dx between -3 and 3 to get the area. Well, how do we do this? First, we need to obtain some knowledge about f. Specifically, we're interested in the roots of f. That will make things a lot easier. This f of x, again, is 1/4 x squared minus 1. The first thing we do is we compute the roots. In this case, that is very easy because that can be written as x over 2 squared minus 1 squared. And then we just need to apply a binomial theorem. And we can reformulate that as x over 2 minus 1 times x over 2 plus 1. And now that, obviously, we can take out a factor of 1 over 2 here and here, of course, also from that whole expression. So we get 1 over 2 times 1 over 2, that's 1 over 4. And then we have x minus 2 and x plus 2. So here we can see the roots clearly. The roots of this function are 2 and minus 2. Right? And that means the function roughly looks like the following. Let's make a quick sketch here. So let's see, you want the interval from this is -1, -2, -3. So here's the boundary of our interval. That's 0. Here's 1, 2, 3. So that's the other side. And now about the function, we have roots at 2 and -2. At the point 0, the function value will be -1. And we can also compute the function value at the point 3, of course. That will be, let's see, if we substitute 3 in here, we get 3 minus 2, that's 1, and 3 plus 2, that's 5, so it's 5/4. Okay, so we have, this is roughly here, and the same is true for -3, that's roughly here. Right, so this is f of 3 is 5/4. Now we can make a sketch of the function. So roughly the function will look somewhat like this. So the areas we are looking for, well, here's our boundaries. So we have these two areas here, the positive parts. And then we have this area here that's negatively counted in the integral. So if you want to integrate over the absolute value, then we have to change that function here. I'll make the following adaptation. So here in this area, the absolute value is the same because the function value is positive. In between those 2 points, we basically flip it up. So do something like this, right? So this is the absolute value of the function f. And now we can finally write down the integral. So we know that this integral from -3 to 3 over the absolute value of f of x dx, that can be split up into 3 areas. The first one is from -3 to -2 to the root, where the function is positive. That means we can just integrate over f of x dx. Then we integrate from -2 to +2. The function is negative here, so the absolute value is minus f of x dx. And then we integrate from 2 to 3, and here we again have f of x dx. So that is what we have to do, and now we just need to execute that. Remember the function f, let's write that down once again, there was 1/4 x squared minus 1. So integrating that should not be too hard. Let's do that. So what we get is integrating f means we have integrating x squared yields x to the power of 3 over 3. So that gives us this 1 over 4, of course, times x to the power of 3 over 3 minus 1. And 1 integrated is just x. So that is the integral that we're looking for. And we have that from -3 to -2. Then we integrate the negative of that. So we get minus x to the power of 3 over 4 times 3 plus x from -2 to 2. And finally, x to the power of 3 over 4 times 3 minus x from 2 to 3. Now we just need to do the computations. And as you'll see, what we get here is, let's see, 4 times 3 is 12. Minus 2 to the power of 3 is -8, so we get -8 over 12 plus 2. And then we subtract the function evaluated at the lower bound of -3. So that is minus 3 to the power of 3, that's 27, minus 27 over 12. Minus 3 and another minus, so that's a -3 here. Okay, so that's this one part here. Then we get the middle part. Upper bound, that's again 2 to the power of 3, that's 8. So minus 8 over 12 plus 2 plus the lower bound, minus 8 over 12 minus minus 2, so that's again a plus 2. And finally, that last part here, plus. So that's again the upper bound here. So we have 27 over 12 minus 3 minus 8 over 12 plus 2. Okay, and now we just do the computations here. So all in all, if we add all that up, the result that you should get is 23 over 6. Just keeping this short. You can all type this into your pocket calculator if you want, or do the computations by hand. It's not that hard, it just takes 2 or 3 minutes. Okay, so this is the area. And again, be careful, we need to integrate over the absolute value of the function f here, right? Not over f itself, because that also has positive and negative area parts. So the integral would not be 23 over 6. As a little practice exam, just try that out. Maybe you'll hopefully find out that this will yield a different value. Okay, now we have computed some integrals, and you will have noticed probably that the arguments of the functions that we looked at were pretty easy. So for example, here we have a sine of pi x. We didn't combine that with anything. No sine of pi x squared or something like that, or even something like sine times cosine. Here also, right, we have e of minus 2x, nothing like x squared e of minus 2x or something like that. Of course, this method of just guessing the right antiderivative and then verifying it's right and maybe correcting for some little quirks works in lots of situations, but it may not work in every situation. So that's why we need some more sophisticated integration rules that can help us deal with more complex integrals. And we'll talk about some of these rules in the upcoming videos. As usually, I'll see you then.